So as I said, I will talk about electrical steels and in particular grain-oriented electrical steels. I hope I'm loud enough when I talk, otherwise you can turn me up maybe. The talk will be on electrical steels. I will give you some ideas about transformer design, which you can use in order to make the best of our steel grades and meet the future efficiency regulations, and try to go on with some technical commercial conclusions. First of all, why is ArcelorMittal committed in the business of electrical steel? Our company is the biggest steel company worldwide, but has a strong interest in being a sustainable business. So we have been investing a lot of money in making steel with a low CO2 emissions and by improving our processes. And the business of electrical steels is in fact complementary to that, because with the electrical steels we can produce energy in a green way via hydro generators, via wind generators, and we're also involved in the business of electric and hybrid vehicles. This is why, although the business is small compared to the global output of ArcelorMittal, it is considered an important one. We have electrical steels in different parts of the world. We produce cold-rolled motor laminations in the United States and Canada. We produce most of our steels in Europe, but we also have a site in Brazil. That is in fact ArcelorMittal together with Aperam. We are not only producing iron silicon alloys, which are called electrical steels. We also have in our group an offer in iron nickel and iron cobalt alloys, who are produced in France. And in this way we are in fact the only group worldwide who can offer both the solutions in iron silicon and iron cobalt, which is for some businesses interesting, like Formula One cars who use both materials, where we also have supplies. The major discussion will be regarding the Friedek-Mistek electrical steels of the grain-oriented. Friedek-Mistek is located in the Czech Republic and has made some developments which I'm going to present now. Just to situate the product, grain-oriented is obviously used in transformers. For those who wouldn't know how a transformer works, obviously there is the steel core. I'm sorry, the pointer doesn't work. So there is a steel core with copper windings. One side is the low voltage end, the other side is the high voltage end. The target of the electrical steel is in fact to transform as much energy as possible with as least losses as possible. The electrical losses, the magnetic losses you make will reduce the efficiency of the transformer, and if we can create steels with high polarization levels, the energy transfer will be more efficient. The most important element that came up in Europe this year was in fact quite recent. There's been the publication in May 2014 of the one lot of the European Commission's Eco-Design Directive, and it is the regulation on transformers in the context of energy-related products. We were in the working group and we helped define these new regulations and to push them into a way that they would improve transformer efficiency in a reasonable way for industry. What is important in this eco-design regulation is that they divided the transformer classes in three groups, in fact. It's called the large power transformers, the medium power transformers, and then the small power transformers. The calculations we made with the different parties involved showed that the gain in CO2 production or in less energy use that Europe could make by putting an efficiency regulation on the medium and large power transformers was already quite important, and therefore the European Commission decided to define minimal efficiency performance levels for the medium and the large power transformers. This was not done for the small power transformers. The whole idea was based on doing life cycle analysis and life cycle costing. That is to check how much your investment cost will be compared to the cost or energy use during the life of the transformers, and then to also take care of the end disposal. and this is going to be the basic element in the presentation I make, that is to compare the analysis over the life of maybe a transformer with a new material and a transformer with an older material, and how it can improve your transformer use. The point really is that if you look at the levels imposed for the large and medium power transformers, and you look at a longer time grid, it is making the market shift towards a higher performance grain-oriented materials, and notably the higher permeability grain-oriented materials. I'm also going to make a point on small power transformers. Even though there is no new regulations on the efficiency levels, it still is quite interesting to check whether, when you do a whole life analysis, whether by making maybe a slightly higher investment, you can save on the whole cost of the transformer life. And that's what I will show. So the medium power transformers have an efficiency level which is defined by the maximum load losses, that is the losses at full load, in fact, PK, and the losses at no load, which have to also satisfy a maximum level. And those are the two elements we use for the cases we calculated with the materials we have. This is just a copy of our catalog. In fact, this page is in the whole group of conventional grain-oriented materials, those with a letter S in the end, which are available in thicknesses from 0.35 to 0.23 millimeters. And you can see the loss levels in the first number at 1.7 Tesla and 50 Hertz. The one I've cycled is the red one, which is nowadays like the basic grade in the market, and it's being used as the reference for the rest of the calculations I will show. The newer conventional grain-oriented materials we have developed are what we called improved conventional materials. We have them available also in the same gauges, 0.35 to 0.23 millimeter, and they come with lower losses than the table you just saw, and they also come with a higher guarantee polarization level. So these grades in fact put you somewhere in between the conventional, the CGO grades, and the high permeability grades in the standards. And the point what I want to show is how can you make use of such grades. There will be two case studies. One case study falls in the area of the medium power transformers, and one case study works in the area of the small power transformers. That is basically where we target to put the improved CGO materials. You can see the specification of the transformer over here. What I really want to point out is that in the case of the medium power transformer, we work with strips that are just longitudinally cut strips, and all of the strips are used in the longitudinal direction. In the case I will detail later for the small power transformers, it is a design using the E and I shaped laminations, so there will be a combination of longitudinal and transverse properties that are being used. This is also interesting, therefore, to make a comparison with a non-oriented material, so one with a letter A in the end. A 230-35 is a non-oriented material which can quite easily be swapped with an M155-35, but I would like to point out a little bit better what exactly the impact of such a swap is. Here you can see the basic philosophy of how we made the designs. We used obviously a 2D design for a transformer with the steel in purple and the copper windings in orange. And we made, in fact, a fixed 2D design. When we swapped the materials and tried to put the transformer in another working point to see how it reaches a specific power level or efficiency level, we just made a variation of the stack height. That's quite reasonable for the understanding and makes the comparison more physically logical. Here is the first case study regarding the medium power transformer. This is a little copy of the case we chose. So it's a 10 kilovolts to 400 volts transformer with 1 MVA as power level, and so it fits between the 5 and the 40 of the medium power class, and it has as necessary maximum full load losses 9,000 watts, both in the tier 1 case, which needs to be satisfied in 2015, and in the tier 2 case, which needs to be satisfied in 2021. The difference is, in fact, that as you go along in time, the no load losses need to be further reduced. You can see here the magnetization curves, and by the way, you can have all the data files from all our materials if you come over to our stand afterwards, so you can do your technical calculations. You can see the blue line is in fact the older material, the 15535S, which obviously has the lowest polarization curve and the highest loss curve. What I also want to point out is that all of the grain-oriented materials are made with a similar alloy content, which means that they will all evolve towards the same saturation polarization, which is only defined by the chemistry. And so you have in this area of use, you can change the working point and benefit from the better properties. If you push your machine or your transformer too much into saturation, you will not see much difference between any grain-oriented, but that nobody is normally doing that. What I also did when we did these calculations is we defined the different working points depending on the graphs that we just showed. So for the older material, 1.6 Tesla, and for the newer materials, 1.7. I'll just come back to this graph. It's reasonable to put your transformer's working point at about the knee point, and so the knee point for this material is about 1.6, and the knee point of the other materials is higher. So that explains the 1.6, the 1.7. And furthermore, in this comparison, it's nice to see that with a different working point, you do have the same losses. So you will have here a higher polarization level, a higher flux, and still the same losses. Obviously, the stacking factor is defined by the thickness and will only be changing when you go towards the lower thickness grade. Now, there are several cases that we studied. We took here the new grade 12535S and defined the transformer geometry that allowed to reach the tier 1 targets with a bit of margin, so 10 watt extra on the no load losses, 50 watt extra on the full load losses. Then we changed the stack height and varied in order to reach identical full load losses with the older material and also with the thinner material. And again, with the thinner material, we changed the design in order to reach also tier 2. Tier 2, as I remind, was normally thought to be essentially a target you could reach with high permeability grain-oriented, but it will be shown that you can reach it also with these grades. Here is the performance. Try to explain you the graph. So we have here the loading. This is the no load level. Obviously here we have at the other end the full load level. You will see from this graph that it's very important to know the duty cycle of your transformer, and that your choice, your optimal choice, will depend on whether your transformer will be used essentially at a close to full load, high load as we call it, or if your transformer is essentially going to be at a low load level, or possibly also the transformer doesn't work but it's still connected to the grid and it will consume no load losses. This situation is in particular used in countries where there is not so much switching gear and they leave all the transformers on the grid, whereas we in Europe have normally the habit of taking them off the grid when we don't need them. I will show you first of all that obviously the highest losses are reached with situation B, which is the old material. Then with the new materials, you can see the red and the green solution, changing the thickness, where you have the same full load losses, but you can reduce the no load losses. And on the other hand, with the orange solution, you can have even also lower full load losses. So the best, although this table is a bit heavy to read, but I'll try to explain it a little bit further. We have in fact calculated 4 cases, and if you look at the geometry, so the transformer design, the essential difference will be the stack height, which is 0.185 for the older material, and is then changed in order to make the different designs for the newer material. What you can see is with the changes of designs, we need a different mass of copper and a different mass of steel, and that with the use of the 10523S material, we have identified what we call a minimum investment cost. It's in fact a quantification of the cost in a very rough way. We consider that copper is about 7 times more expensive than steel, and take those masses then together and use this to identify what the total mass of active material is going to be, and relate it sort of to costs. This transformer so has the lowest no load losses, and it manages to reach the tier 2 targets. If you then, on the other hand, go for the last column, you can see that the transformer has become bigger, and this is necessary in order to further reduce the full load losses. It also reaches the tier 2 target. And the point really will be, do I take solution C, so this one, do I take this solution? It all depends on what you want to do with your transformer. Is it going to be very much operational, not full load, or is it rather going to be used at lower load levels? And that will make you choose between the different designs, and hence in the investment cost. So you have to balance the investment cost with your exploitation cost. And that's a little bit what I tried to write down here. I think it's what I already said, so I'll skip this slide. Just trying to show you that you really have to think carefully before you go into one or another option. The next case is a small transformer, as I said, with a typical EU design, which means that the I part, the I part is cut into the longitudinal direction, the rolling direction, also these legs, but here you will see the transverse direction, and in between you will have rotational losses. That is a situation which can be tricky for transformers and can create unexpected efficiency loss if you didn't take it into account properly. So it's a small transformer, as I said, 10 kVA. Now, the materials that we chose, as I said, we made in this case a comparison with non-oriented material. So in green you have the non-oriented material, the longitudinal and the transverse direction. You can see that the green curves are in between the red and the blue of the grain-oriented materials. The non-oriented material is more isotropic, so you will have losses longitudinally and transversely that are quite equal. The grain-oriented material will have a very good polarization in the longitudinal direction and not such a good polarization in the transverse direction. And it's a similar situation in terms of losses. It looks like this one is in between compared to the longitudinal losses and the transverse losses. So it's interesting to see where it brings us when we make the full calculation. Logically, again, we adapted the working point according to the magnetization curves. So for the fully processed, it is lower than it is for the old grain-oriented, and lower than for the new grain-oriented. And you see for the grain-oriented that obviously you have here lower losses. The stacking factors are the same because all of the materials are 0.35 millimeter in gauge. The point here is that we also did a similar transformer optimization by changing the stack height and used different materials in order to reach different efficiency targets. The results, again, are shown first of all in a graph. It's quite easy in this case because when you switch from the non-oriented material, you have in fact the highest losses, so the least efficiency. And if you switch to the older grain-oriented, it gets better, and it gets better still with the new grain-oriented. What's interesting to see is that it's essentially a benefit that you get with the newer grain-oriented material if the transformer is often used at low loading, which is quite often the case for such a small industry transformer. And again, a table with all the data. The stack height is the one that has been varied, and we come to the point that if you look at the total amount of material used, the best investment would be to go for the new grain-oriented material. It gives you the minimum no load losses, and it gives you the minimum overall exploitation costs. So it does make sense, even for a small transformer, to think a bit further what kind of materials you put in there, and to make a little study and to decide on what is your best choice. And obviously take into account whether you are allowed to make the transformer a bit bigger or whether it's not allowed, and what exactly your targets will be. The other part, which is often discussed regarding grain-oriented transformers, is obviously the transformer noise. That's one of the reasons why I put a non-oriented material in the comparison, because we all know that the noise is in fact linked to the induction or the polarization level to the square. If you take just the magnetization forces into account, which means that when you work with a higher working point in a grain-oriented, you will create more noise. Obviously, there's also noise coming from different other aspects, such as the way the transformer is built together, how the overlap is done in the laminations, and so on. But if you want to talk about the intrinsic material properties, you have to take the polarization level into account. I've just given here some data on magnetostriction coefficients of grain-oriented material and non-oriented material. The grain-oriented material has obviously a different magnetostriction in the two directions, and which is linked to the texture, because it has a lot of 110 texture. The non-oriented material is quite isotropic with, and on the overall, a lesser magnetostriction. Which means that if we go back, maybe I should go back to this graph. When we switch from the non-oriented towards the grain-oriented, we certainly can improve on efficiency. If you're worried about transformer noise, then maybe there is another optimal choice to be made. We can help you out with further calculation and detail support if you need to look into this in more detail, but I only had 20 minutes to talk, so I'm trying to be a bit brief. So I come to the general conclusions. We have improved the grain-oriented material performance. We have shown that it is possible with the new materials to reach the efficiency regulation of the European Commission, not only for the target in 2015, but also in 2021, if you accept to make a design change. And we do machine calculations, we do magnetostriction measurements, whatever you need to help your choice in material, we can help you with. Okay?
Well, thank you very much indeed for that session, which was full of interesting points. Now, would anyone like to ask a question or make a comment, please? And if you can you see the man with the microphone and give your name and make the question as short as possible, please? Anybody?
Yes.
Good morning, Dominique Papazian, our group. Have you made some trials with a 0.18 millimeter thickness magnetic strips?
Yes.
To check with 0.23 and see what is the result?
We don't produce 0.18 millimeter grain oriented so far. We have looked more into the needs of our customers, and what we have seen is that it's very often a choice between cost and performance. And for us, the need to go into 0.18 didn't seem as pressing as the need to go into thicker grain-oriented materials. So we have not done this development so far.
Okay, so you don't think to develop this in looking to 2021 regulation?
Yes. I think it's not worth the effort of doing it on the grades that we are doing right now. It's if you want to compete with amorphous material on high permeability grades, I see there is a point in going into 0.18. It will increase the cost a lot, but amorphous material is very expensive. So there you can probably find a target. In this case, we are looking rather at improving the conventional grain-oriented materials, and we don't really aim for the same market as the market which is being served by 0.18 millimeter grain-oriented. It's all a matter of strategy, and I think it's just a choice.
Okay, thank you.
Anybody else? Well, perhaps I could ask something that might spark off something. In terms of your relationships with customers, you have global customers. Are they becoming more demanding, less demanding over the years, or about the same? Maybe you can talk about the interaction generally.
Well, the customers, they obviously are becoming more demanding, but it's on different levels. It's on the quality, the stability of the product. It's obviously also on loss levels and polarization level, which is the aspect that I showed now. And then there's obviously also the fit to market, which is something we've been looking into with the European Commission working groups in much more detail, hence the life cycle analysis, the life cycle costing. And the last point I made, obviously the noise is becoming more and more critical. There are more transformers put into environmentals where there are people living around it, and there's also a big evolution in terms of transformer noise work.
And are there parts of the world where you find the requirements by the customers that much more demanding?
Well, if you look at the new regulations in Europe, they're quite similar as the regulations in the US, as in Japan, as in Australia. I wouldn't say there is a particular pressure from the different governments to go to different efficiency levels. It's rather habits of the market. Certain parts of the world are using more conventional materials, and there is a history behind it also.
Okay. Anybody else got any points they'd like to make? I mean, I can think of one or two other questions to ask Sigrid, but I was hoping somebody else would have something to say. Well, but perhaps I could just ask you one thing which I'd be interested in, the competition amongst other steel companies. Obviously there's more steel companies as the world goes on. Are you finding there are more and more people to be worried about who can make your grades of technical steel as time goes on?
I think we're all doing our developments, and we're all working according to our metallurgical principles, and we're all pushing forwards, and can't really. Obviously there's dynamics worldwide, but everybody follows their own principles and continues working, obviously.
Okay. Right. Okay. Well, look. If there aren't any more questions, we can end this session here, and we'll have a bit more time to have a bit more of a break until the next session. But perhaps just give Sigrid another round of applause, please. Thank you.